Assalamu alaikum everyone. So this is the 10th lecture of the course Wireless Networks, and this is the second part of the topic Wireless Local Area Networks, and we're going to start where we left off. Just a brief overview of what we did and what we're going to do. So previously in the last lecture we learned about the scope of 802.11, the different levels of the reference model, the architecture, and we also learned the services, and we learned some part of the frame formats, okay, and we skipped the physical layer part, but then we started with medium access control protocol. Okay, so this is where we are currently. We are learning about medium access control protocol, or MAC protocol of 802.11. so in the last lecture we started learning about timing and interframe spaces and the 4 different types of interframe spaces: short interframe space, point coordination function interframe space, distributed coordination function interframe space, and extended interframe space. Okay, and then we saw a figure, right, and we stopped here. So let's start from here again. So in this figure what you can see is at the very beginning the channel was busy, and just after the data was sent, an SIFS period of time, the nodes waited. Okay, so this is short interframe space, and just after that an acknowledgement was given. Okay, so when an acknowledgement is given by any of the nodes, the other nodes understand that one data packet has been finished transmitting. Okay, so now the channel should be idle. Okay, so as you can see, this is where the interframe spaces come into play, and different nodes wait for different interframe spaces. For example, as you can see here, SIFS, PIFS and DIFS, all of them are stacked together here. So that means depending on which node is trying to access the channel, it has to wait for an SIFS period of time, PIFS period of time, or DIFS period of time. Okay, and after that the contention window starts, and I think you already know about the contention window by now. So for 802.11 the contention window starts from 15 slots at the beginning. Okay, and just after contention window, if the channel was busy throughout this entire period, then it starts sending the RTS, or request to send, and after an RTS it waits again for an SIFS time period to receive the CTS. Okay, and during this time the receiving node, if it is free, then it will send CTS, or clear to send, and after receiving a clear to send, then the node will again wait for an SIFS time period and then send a data packet. Okay, so as you can see here, in all of these different places, everywhere, almost everywhere, SIFS is used, and only in the beginning when you want to send a message and you want to start your countdown, only at that time DIFS, PIFS or SIFS is used. Okay, so we're going to learn about these differences and when they are used. So as I've already said, SIFS is short interframe space, and when you are usually waiting for SIFS time, you do not wait for clear channel assessment or carrier sensing. Okay, for example, in this scenario, just after RTS you are directly sending a CTS, so you're not checking the channel whether it's busy or not, you directly send a CTS. Okay, similarly, before sending an acknowledgement, you wait for an SIFS time period, but you do not check for the channel. Okay, you directly send an acknowledgement. Okay, only during this period, the contention window period, you only check for whether the channel is busy or not. Okay, so this is a short overview of how each of these interframe spaces compare in lengths. Okay, so at the very beginning we have SIFS. Okay, and PIFS is actually just SIFS with a slot time. Okay, so what is the slot time? A slot time is actually this period. Okay, as you can see here, there are 15 slots in this contention window, right? Okay, let's just count them: 1 2 3 4 5 6 7 8 9 10 11 12. Okay, so it shows that there are 12 slots here, but the maximum that you can do here is 15 slots. Okay, so for and you can select a random number from 0 to 15. If you already know that, right? You should already know that. So the random number selected in this scenario was 12, which is why there are 12 slots here, and each slot has a time period of 9 microseconds. Okay, so from this you should understand that PIFS is actually just 9 microseconds more than SIFS, again DIFS is 1 slot time more, that means 9 microseconds more compared to PIFS. Okay, and as SIFS is too short for clear channel assessment, so only there is no clear channel assessment, only the this time is only used, you know, for small short break, so that this time can be taken for the transceiver to start sending instead of receiving. Okay, just this changing. So these are all the details of the different time periods. So as you can see here, a slot time is used to calculate interframe spaces, and this is actually the SIFS and a slot time. Okay, the slot time, these two are the basis of all the other durations, and in 802.11a the slot time period is 9 microseconds, as I've already said. So SIFS is used to prioritize the immediate acknowledgement of a data frame, as we've already seen, right? And the response, that means CTS to an RTS. Okay, so this is the fastest interframe space, and this is used in these cases when you want to immediately send an acknowledgement, or when you want to immediately send a clear to send after someone sends a request to send. Okay, so a subsequent MPDU of a fragmented MSD. Okay, so what does this mean? Okay, to learn this we have to understand fragmentation, so we'll learn about this more when we see fragmentation. Okay, so this is also used as a response to any polling using the PCF. We'll also learn about this later on because we haven't seen polling yet. And it is also used for any frames of the access point during CFP. Okay, so CFP is one phase, we learn about this phase later on. And this SIFS is also used by the access point during CFP, because the access point has the most priority compared to all the other nodes. Okay, so only the access point starts its contention window with SIFS time. All the other nodes start with PIFS time or DIFS time. Okay, so SIFS time period is 16 microseconds for 802.11. Okay, so PIFS is used by all the stations operating under the PCF or point coordination function to obtain channel access with highest priority, as I already said. Okay, and PIFS is SIFS plus slot time, and SIFS is 16 microseconds and a slot time is 9 microseconds, right? So PIFS is 25 microseconds. DIFS is used for stations operating under the DCF, that means distributed coordination function. Okay, to obtain channel access, and DIFS is equivalent to SIFS plus 2 slot time, or if you follow the previous definition, then DIFS is equal to PIFS plus 1 slot time, right? So let's calculate for this scenario. So SIFS is 16 microsecond and a slot time is 9 microseconds, so 2 into 9 is 18 microseconds plus 16 microseconds, so the total is 34 microseconds for DIFS. Okay, so we have seen all the interframe spaces here, right? But we are just missing one interframe space, which is the extended interframe space, right? So as you can see here, the EIFs, which we already learned here, right? The fourth one, that's not here, right? Because it's not used in normal scenarios. So let's see what EIFS is, or extended interframe space is. So EIFS is used instead of DIFS when multiple stations initiated frame exchanges at different starting times, typically due to they are hidden from each other. Okay, so we are talking about hidden stations now. I think you already know about hidden station problem, so I'm not going to explain that in detail now. So this means that the scenario rises when there are hidden nodes, okay, and all of them started using DIFS. Okay, sorry, all of them are trying to access the network, okay, or access the channel. And during that time, instead of DIFS, EIFS is used. But when? So EIFS results in a longer deferral from channel access, which gives other stations a higher priority in medium access. As soon as one other frame is received correctly, DIFS is used again. And EIFS is around 200 microseconds for 802.11a. Okay, so what we've seen before, if you compare to these interframe spaces, this is huge, right? 200 microseconds. So why this is so huge and why is it used? Okay, so in case of hidden stations, whenever multiple nodes try to access the channel and they are facing collisions again and again, okay, but they are not able to sync with each other because they are hidden from each other. Okay, to solve this problem, EIFS is used. So when there are multiple times there are collisions, all the nodes who are facing collisions, they wait for EIFS time. Okay, and during this time, all the other nodes who were not able to send their message use this time period to send their messages. Okay, So this is used instead of DIFS when multiple stations initiated frame exchanges at different starting times, okay, typically due to they are hidden from each other, okay. Although it says the different starting times, it means that they are randomized, but even then they are facing collision, okay. To solve this problem, EIFs is used. So next, let's see about the collision avoidance technique for 802.11. And one thing, okay, so if you remember, we saw that 802.11a here, right? So this means is the very first version of 802.1 and the most dominant version, okay. So a collision happens when there are more than one station attempts to transmit at the same time, right? You already know what collision is. And in wireless communication, transmitter cannot detect collision at receiver while transmitting. Why is this? Because a transmitter cannot, we use transceiver in case of wireless communication, right? And the transceiver, while it is sending, it cannot receive at the same time. As a result, the transmitter cannot detect collision while at receiver while transmitting, because it's actually transmitting and at the same time it has to receive to understand whether there is a collision or not, which is why it is not able to understand a collision. So collision detection is not possible here. To account for this, 802.11 is based on CSMA collision avoidance, okay. So I think you already know these two types of CSMA, carrier sense medium access, right? One is collision avoidance and one is collision detection. So collision detection is used mainly for wired networks because it is easy to detect a collision, but in case of wireless networks it is difficult to detect a collision due to various reasons. One is which I already mentioned, and also because of signal power decrease from time to time, okay. So in this scenario, in wireless networks, we use collision avoidance, okay. So if two or more stations detect the channel as being idle at the same time, inevitably both the stations start transmitting at the same time, right? And that is when collision occurs. And 802.11 defines a collision avoidance mechanism to reduce the probability of such collisions, and we are going to see what this collision avoidance mechanism is, okay. So part of collision avoidance is a station performs the backoff procedure before starting a transmission, okay. So the backoff procedure, that is what we know as the window, okay. So let's go back, this contention window. So this is called the backoff procedure, okay. So this includes the contention window. So let's go deeper what the backoff procedure means. So a station having an MSDU to deliver has to keep sensing the channel for an additional random time, which is the backoff time, right? And the maximum is 15. So randomly, if you select a number, for example, let's say the random number is 7, then the backoff period should be 7 slot times, and after detecting the channel as being idle for at least DIFS. So before starting the backoff or the contention window, it has to wait for DIFS time. So the duration of backoff is n into slot time. So n is the random number which has been selected, and the slot time is, as you already know, 9 microseconds. So each station maintains a so-called contention window, which we already saw, right? Which is used to determine n. So n will be greater than or equal to 0, and it should be less than or equal to the contention window size, okay. So in 802.11 the contention window size is 15 slots. So this is an example actually. So in this example, after a successful frame exchange, which is here, station wants to send another data frame. It starts transmitting RTS after sensing the channel is idle for a duration equivalent to DIFS, okay. So this DIFS, and it's following backoff slots, which is this contention window, okay. So you know about this already, but still just a brief recap. So after an unsuccessful transmission, the next backoff is performed the double size of the contention window. So previously the contention window, or the initial contention window size is 15, right? So even then if there is a collision, it doubles. That means now the contention window size should be 31, okay. So it's 0 to 15, that means 16 slots. So now it will be 0 to 31, which is 32 slots. So this reduces the collision probability if there are multiple stations attempting to access the channel. Is it clear? So as you can see here, this figure shows it, the very first collision, and this is the first scenario. And now if there is a collision, then again for the nth scenario it will start with the contention window 2 to the power n minus 1, okay. So this is just a formula for a repeated frame if you are facing multiple collisions. Okay, so now we were talking about the stations which faced collisions, right? But there were some other nodes as well which were trying to send their message. What happens in their case? So they were not able to finish their contention window time period because someone else started sending the message. Okay, so for them what will happen? The station that deferred from channel access during the channel busy period do not select a new random backoff time. Okay, so this is very important. So but continue to count down the time of previous backoff after sensing the channel as idle again. So let me explain this again. So let's say station A is trying to send a message, but it faced a collision, right? And say station B was also trying to send a message, but before it could finish the contention window, station A started sending the message. So if the contention window size or the random number selected for station B was 10, and let's assume that after counting down to 5, station A started sending, so station B could not send. So after station A finishes, or after the collision finishes, then station B will start immediately from 5, not from 10. Okay, it will not select a new random number, it will directly start from the backup that it stopped to previously. So if it was starting with 10 previously and then it stopped up to 5, now it will again start from 5 and not from 10. It will start from the previous stopped position. So in this way, stations which deferred from medium access because the random backoff was larger than others are given a higher priority when they resume the transmission attempt. So this actually stops starving of the packets or of the nodes. Okay, so there are some recovery procedures and retransmission procedures as well. So this is done when there is a collision. Okay, so how does it work? When a frame exchange is not successful, the size of the frame is compared against the threshold value before retransmission. Okay, so let's say the size is greater than a certain threshold, then it is considered as a long frame, and if it is lesser than the threshold, then it's considered as the short frame. Okay, so it says that if the size is less than threshold, then increment the short retry counter. Okay, and if it was the first frame, that means the RTS frame, then is automatically included inside the short frame. Okay, so when the size is less than threshold and there was a collision, then the short retry counter is incremented, and if it is greater than a threshold, then the long retry counter is incremented. Okay, so the increment depends on the size of the frame. The frame is discarded when SRC, that means the short retry counter, or LRC, that means the long retry counter, reaches a limit. For example, the default limit is 7 for short frames and 4 for long frames. That means if you are facing collision for 7 times and the frame is a short frame, then you will discard the frame. And if you are facing collision for 4 times and the frame you are using is a long frame, then you will discard the frame. Okay, when the limit is reached. Okay, so there are 2 different limits for 2 types of frames. This is done so that the long frames are discarded easily because they require a lot more time to send compared to short frames. So whenever an MSDU is successfully transmitted, the SRC and the LRC are reset. Okay, obviously. So when a successful transmission is done, both the counters are reset to 0. So the threshold implementation is implementation dependent. Okay. So what is post backoff? Okay, so after each successful transmission, it is mandatory that another random backoff is performed even if there is no other MSDU to be delivered at the station. Okay, so we know what normal backoff is, right? Backoff is used when you want to send a message, but post backoff is if you have transmitted your data packet and you do not have any other packet to send, even then you will be performing a backoff. Okay, and as this backoff is done after transmission, this is why it is called a post backoff. So why is a post backoff done? Because you do not know when you have to send a frame. Okay, so let's say you have a frame to send and that suddenly came to you, so you have to start the backoff from the beginning, right? But if you are doing a post backoff, then you are already inside a backoff, right? And you do not need to start a backoff again. So when you receive the frame, you can directly send it using the current backoff that you are performing. Okay, this is one reason. Another reason is it reduces the delivery delay in lightly loaded systems, okay, because it doesn't have to start backup from the beginning. The overall throughput of the network or delay of a specific node is decreased, okay, and then the overall throughput is increased for lightly loaded systems. Remember, okay, because if the system is highly loaded, that means there is too much traffic, then this will not help that much. And it is also guaranteed using Postbackoff that all the frames will always be delivered with backoff and no frames will be delivered without backoff. So next we're going to see fragmentation, as I've already told you before, right? There was some aspect of interframe space, or when interframe spaces are used, related to fragmentation. So what is fragmentation? It is the process of partitioning an MSDU into smaller MPDUs when its length exceeds a certain fragmentation threshold, okay? So if you remember, MSDU is MAC service data unit and MPDU is MAC protocol data unit. So the difference between MSDU and MPDU is when MSDU is added with a header, then it becomes MPDU. So if the MSDU is huge and it has to be broken down into smaller parts, and for each of those parts a header is attached, then we can say that an MSDU is broken down into smaller MPDUs, and this is actually called fragmentation process, okay? So the benefit of fragmentation is that if there is a failed transmission, you do not have to start sending the packet again from the beginning, okay? So there is a lot of time saved, because let's say even if there's a failure in one part of an MSDU, you do not have to send the entire MSDU. That is one reason. Another reason is if you face a collision, or let's say an error or a failure, then you can detect that after sending the entire packet. So the entire MSDU becomes too large and you have to waste the channel for a longer time. But if it is a fragmented packet, then you detect earlier that there is an error, okay? So if you have any confusion regarding this, obviously you can ask question later on as well. So the obvious drawback is there is an increased overhead. Why? Because if you are successful in sending a message, then MSDU is actually faster because there is only one packet and one header file. But if it is broken down into separate MPDUs, there are many headers, and each of those packets need to be sent after a specific interval of time, right? Which is why the drawback is the increased overhead. But it is very useful when you might have errors in the channel, which is actually always the case when you're working with wireless networks. So this is an example of fragmentation, and the process of recombining MPDUs into a single MSDU is also called defragmentation, just the opposite of fragmentation, okay? So only MPDUs with a unicast receiver address may be fragmented, okay? Because if it is broadcasted, then you do not know, okay, which message is going where and which message was missed. So it's very difficult to track. And if it is fragmented, then broadcast already floods the channel. So if MSDU is broken down into many MPDUs, then it will be a more huge flood compared to before, right? And the maximum length of an MSDU is limited to 2346 byte, okay? And after that it will be broken down into smaller parts, okay? So let's see the example. So at the very beginning you can see the nav was reset fine, and then after waiting for DIFS time, which is the case for DCF, distributed coordination function, it waited for a random backoff. In this scenario it's 6 slots, right? And the station 3 also started the same time, but its random backoff time is 8 slots. So actually station 2 will start sending before station 3. So it started sending its data 1, right? Then it waited for SIFS period of time. During that time, station 1 sent the first acknowledgement, okay? Then again it will wait for SIFS time and again send the second data packet, okay? Again it will wait for SIFS time and get the acknowledgement. So as you can see, if it was a normal data packet, then what would have happened? After sending the data and receiving an acknowledgement, then again all the other nodes will start contending for the channel, and station 2 will also start contending for the channel. But now, as it is a fragmented packet, it keeps sending the packet until all of it is sent, and during each data packet interval it only waits for SIFS time for the acknowledgement, and again after SIFS time it starts sending the data, okay? So as you can see, this is an example of a fragmented data packet, and during this entire time the station 3 will be waiting for the other station 2 to finish. but the channel might be free for the middle of the time, right? But even then it will be waiting because it has been told to wait using nav. Okay, as we have already learned that using nav the other nodes can be told to stop and the channel can be made to seem busy virtually. So next is hidden stations and RTS and CTS. Okay, so I'm not going to explain this in detail because you already know what hidden stations are, but to solve this hidden station problem, CTS and RTS is used. Okay, so how does this solve the hidden station problem? So in case of hidden station, the problem is the nodes which are closer to the receiver but far away from the transmitter, they do not understand whether the receiver is supposed to receive a transmission or not, and they start sending their own message, which is why there is a collision at the receiver. But now due to RTS and CTS, the receiver also sends a clear to send packet now, right? So if any other node which is closer to the receiver but far away from the transmitter, or in this scenario we call it a hidden station, so hidden station can hear the CTS packet from the receiver, so it doesn't send a message, and this solves the hidden station problem. So this is an example of hidden stations using RTS CTS. So I'm not going to explain this, but if you have any question regarding this, you can ask me and I'll explain this part in the discussion session. Okay, so the next thing is synchronization and cell search. Okay, so synchronization is used for each of the nodes to actually synchronize with the other nodes so that they know when they have to send the data packet, or they can synchronize their clocks or their times. Okay, so there are many things here, but we are not going to learn these things. The only thing important for us is the beacon transmission time. Okay, so all stations within a single BSS or basic service set are synchronized to a common clock via the timing synchronization function, or TSF. To synchronize the station, a management frame which is called the beacon is used. Okay, so what is the beacon? The beacon actually contains the information of each stations. For example, what is the clock time, what is the location or what is the address, what is the node ID, etc. Okay, so these informations are contained inside the beacon, and the beacon is sent after a specific time interval. This time interval is called target beacon transmission time, or TBTT. Okay, so as you can clearly understand, the beacons are transmitted periodically. Okay, so this is the only important thing that we need to understand from this topic. Okay, so the next topic we're going to learn is scanning procedures. Okay, so this scanning procedures uses the TBTT or the beacon that we talked about. Okay, all the other thing that we saw in the previous slides is not important. So let's start with the scanning. So IEEE 802.11 defines two scanning modes. One is passive scanning mode and another is active scanning mode. Okay, so which mode will be applied, this decision is taken by the station management entity, or SME. Okay, and as we have already seen before in the reference model, that SME is a layer independent entity that is spread throughout data link layer and also physical layer. Okay, so it actually resides in the management plane, so it is not in the data plane, which is why the packets used here are management frames. Okay, so let's move on. So the first one is passive scanning. So what is passive scanning? In case of passive scanning, the station or any station monitors each specified channel for a time span of at most max channel time. So what is this max channel time? This is actually the time during which at least one TBTT or one beacon will be transmitted. So it waits and listens for any beacon. So during the scanning, the station adds any received beacon or probe response to its BSS ID scan list. Okay, so what is probe response you don't know yet, but we'll learn a few seconds later on. So what does it do? It waits for any beacon, and whenever it receives any beacon, and as the beacon contains the BSS ID as well, right, the basic service set ID, so it receives that ID and it lists that ID in its own memory. Okay, so that is called the BSS ID scan list. So the scanning duration may vary depending on the number of channels to be scanned. If there are multiple channels, then it has to scan all the channels, right? And it also depends on the load of the system. Okay, so that was passive scanning. In case of active scanning, the station does not wait and listen. It automatically generates a probe frame. Okay, so a probe frame is basically sort of like asking for a beacon. So if you cannot wait for a beacon, you directly ask for the beacon itself. So that asking message or request message is called a probe frame, and then it waits for a probe response. So any node receiving a probe frame understands that someone wants to know my information, and it lets the information known by sending a probe response. Okay, so this is what we saw in the previous slide, right? This was the probe response that we were talking about. So the probe response needs to be acknowledged to ensure integrity of data delivery. Is it clear? So if you just send a probe frame but did not receive any probe response yet, then there is no integrity of the data delivery, so you cannot start sending a message. Okay, so the probe mechanism forces an access point to convey basically the same system information as done with the periodic beacon signal, but without unnecessary waiting times. So if you want to wait for the beacon, then do passive scanning, and if you do not want to wait, you want to directly or forcefully ask for the beacon, then use active scanning. Is it clear? So these are the two different types of scanning. So the next topic that we're going to learn is medium access control with support for quality of service. Okay, and this is a bit difficult to understand, so we are going to finish up to this for now. So for the next class we'll start from this part. Okay, so if you have any questions, feel free to ask. With this I'm going to end today's class or lecture. Assalamu alaikum everyone.